All right, in this video for an AP Statistics review, we're going to review looking for associations between two quantitative variables with scatterplots and correlation. Now, this was a really big unit that covered a lot, so in this video I'm just going to try to hit the main points, and hopefully you remember a lot of it on your own. All right, what we're going to learn in this video is how to describe a scatterplot, how to find the least squares regression line, or the line that we call the least squares regression line. And we're also going to do how to interpret a least squares regression line. And then we're also going to talk about how to read a computer output table to actually understand what the least squares regression line is. All right, so let's take a look at how to read a scatterplot. Anytime you're asked to describe a scatterplot, please, 4 sentences. Talk about direction, form, strength, and a general statement. When we say direction, we simply mean positive or negative. Is the data going up or is the data going down from left to right? Form, we're talking about, is it making a line? Is it making a parabola? Is it making some type of curve? Strength, how strong is the relationship? How strong do we see that form? And then finally, a general statement in context. All right, so here's a look at 5 scatterplots. So if we look at this first one, negative, linear, very strong. Those points are very strong. This one right here is positive, very strong, linear, right? Here's one right here that is going to have a huge parabola, but again, that parabola is actually pretty strong, and it doesn't really have a direction because it's kind of positive, or I'm sorry, negative and then positive, so you would probably describe that. These two here are, for the most part, linear, negative, positive, but again, not as strong because the dots don't form a perfect straight line. Now, the strength is the one thing that's vague. See, direction is very obvious. Positive, negative. Form is pretty easy to see, a parabola or a curve. And then again, the general statement is just to say something like, hey, as the temperature goes up, the amount of ice cream I sell goes down. So something in actual context to the problem. I was just kind of making that up. I don't quite know what these numbers are, but, you know, could be ice cream, right? Who knows? So anyway, correlation actually measures that strength. So correlation is our buddy R here. And correlation is a number that really measures exactly the strength and direction of a linear relationship between two quantitative variables. So there's a lot in that definition, but it measures strength and direction. And it's got to be linear. So like for this graph right here, I would never, ever, ever use R because it's clearly not linear. Now these top 4, they are all fairly linear. Even these ones right here, this one and this one that aren't perfectly linear, that's still fine. They are forming somewhat of a line. So as long as it's linear, somewhat, you could use correlation. Never use correlation. In fact, this graph right here is probably going to have a correlation somewhere around 0 because half the graph's going up and half the graph's going down. Now, they also have to be quantitative variables. Never use the word correlation if one or two of your variables is categorical. So if I tried to say there's a correlation between your height and your eye color, well, I'm the idiot because there's no correlation there. There might be an association. Heck, maybe people with blue eyes are taller. I don't know. But there cannot be a correlation because eye color is categorical. All right, now let's talk really briefly about R. R is on a scale from -1 all the way up to +1. -1 is a perfect down negative association. +1 is a perfectly strong positive, dead straight line, positive association. The closer you get to 0, obviously the weaker you are. 0 would be no relationship whatsoever. No correlation. Like I said, a picture like this parabola would be no correlation because it's not linear. Anything 0.5 or higher, I would say is strong, or the same thing with -0.5 or lower. Okay, it's still strong, it's just negative because the points are going down. So that's a quick thing there on correlation. The cool thing is correlation is very resilient. If you switch your X and Y, correlation stays the same. If you change the units of your X or change the units of your Y, correlation will stay the same. Now, if you remove 1 point, correlation can get weaker or stronger, right? So let's look at this graph up here at the very top left. If I were to add a point like this that clearly does not fit the pattern, that is going to weaken my correlation. If I were to add a point like this that falls in line with my pattern, that will strengthen my correlation. Even if I add a point like this that expands the strength, it expands the relationship, it follows the pattern, that will make my R stronger. But again, a point like this one right here, it's going to make my correlation weaker. So adding or subtracting previous points could create a weaker or stronger correlation. But again, changing units, flipping variables, that does not impact correlation whatsoever. All right, Now let's look at a really bit more of a concrete example. Here we looked at a number of trains. We looked at how many rail cars they had as our X variable, and then we looked at the fuel consumption as our Y variable. And we made a beautiful little scatter plot here. Definitely positive. I would say pretty strong. My guess is, again, we'll actually find out in a second, but my guess is this is maybe a 0.8 or higher. That's a pretty strong relationship. Those points are clearly forming a line, so this is, again, linear. So I talked about positive, I talked about strength, I talked about it's being linear. The last thing I want to do is give that general statement in context. As the number of rail cars get added onto a train, the more fuel it's going to need, right? As the number of rail cars goes up, the fuel consumption of a train also goes up. That's that general statement in context. All right. Now the next thing we want to do is find the least squares regression line, right? Back when you were a little kid, you called that a line of best fit. How can I find that line of best fit right there? Well, there's three ways you could find that line of best fit. By hand, let the calculator do it all, or read a computer output table. All right, so first off, the least squares regression line does look like this. it is your y hat, that's your predicted y. We put that little hat on there to emphasize that it's only a predicted y. We have our y-intercept, b sub 0. Some people call that A, or typically the AP Stats test calls it B sub 0. And then B sub 1 times our X value. B sub 1 is our slope, okay? Now, that's the least squares regression line. How do you have your calculator do all the work? So I'm going to skip to number 2 first. To let your calculator do all the work, all you got to do is go to Stat, hit the Stat button, go to Edit, type in the X variables into list 1, type the Y variables into list 2. I already have that done for you. Then you're pretty much good to go. All you have to do is hit Stat, slide over to Calculate. Now, don't choose number 4 because number 4 is not quite the order we like things. We're going to actually scoot down to number 8 here where it's A plus BX. Now, again, A is what the calculator calls your y-intercept. On the stats test, we call B sub 0. So select this. Make sure you choose the proper list. Your X's are into list 1. Your Y's are in list 2. Leave the frequency list blank, leave the store regression equation blank, and just hit calculate. And it'll tell you the variables you need. So Y is the predicted fuel consumption. X is the number of rail cars we add to a train. A is the A is the y-intercept, 10.6768. And B is your slope, 2.1495. Now you also get your correlation. Now notice I said correlation earlier was like 0.8 or higher, and I was correct. It's much higher actually. It is 0.98, very high correlation there. That's R. And R squared we'll talk about a little bit later, but that is 0.9674. We'll talk about that a little bit later. Now, how could you actually find it by hand? Well, to find a regression equation by hand, you need these formulas here. So the formula for slope is the correlation, R, times the standard deviation of the y values divided by the standard deviation of the x values. And then to find the y-intercept, which again is b sub 0 or a, you need the average of all of your y's minus your slope, so you do have to find slope first, times the average of all of your x's. Now, how do you get all these things? So I need 5 things. I need the standard deviations for both x and y. I need the means for both x and y, and I need my correlation. Well, I already have correlation, right? So that's how you get the correlation, 0.98. So I'm actually going to write that down. Correlation is 0.98. Now, to get the standard deviations and the means, you hit Stat. Remember, you already have the data entered into list 1 and list 2. So you're going to hit Stat, slide over to Calc, go to 2 variable stats, select which one is your x's and which one is your y's. List 1 was my x's, list 2 is my y's. Leave the frequency list blank. Hit calculate, and you'll be a long list here, and you could scroll down. So my x bar is 35.6. That's my average x. 35.6 was the average number of rail cars. The standard deviation of x is s right there. That's 10.42. It's the standard deviation of my x's. Keep scrolling down, and you get the standard deviation of y. The average fuel consumption was 87.2. The standard deviation for y is the s, 22.76. And you also get the min and the max for everything, but you don't need any of that. All right, so that's how you get all the information you need. Once you have all those numbers, you can actually use the formulas to calculate the slope and the y-intercept. Very rarely have I ever seen the AP Stats test do that. What I will say is this. I've seen on the AP Stats test a multiple choice question where they give you everything. They give you the average X, they give you the average Y, they give you the standard deviations, and they even give you correlation. You just have to use them to calculate the values. So just got to remember how to do it. Now the good news is these formulas are given to you on the AP Stats formula sheets. You don't even have to memorize them. All right, the third way to get a least squares regression line is to read a computer output table. So a computer output table is something that looks like this right here, where everything is given to you. All right, now first off, this is a really cool computer output table because they literally just give you the equation right here. The fuel consumption is equal to 10.7, that is your y-intercept, plus 2.5, that is your slope, times the rail cars. Most don't give you that, to be honest. What they're going to do is you're going to look for the word constant. Right next to the word constant is your y-intercept. Always, always, always. So find the word constant, that is your y-intercept, which we call b sub 0, 10.677. Right underneath that is your x variable, that's rail car, that's going to be your x variable, and right next to that is your slope. All right, so our slope, b sub 1, is 2.1495. So that means the predicted fuel consumption is equal to 10.677 plus 2.1495 times x, which is the number of rail cars. Now, what does this equation do for me? Well, you give me how many rail cars. So let's just say a train has 15 rail cars. Okay, I'm going to plug that in for x, and I'm going to do the math. I'm going to multiply by 2.1495, add the 10.677, and that will give me a predicted fuel consumption for that train. So very, very easy. So that's what I have down here in yellow. What is a least squares regression line for? It's used to predict a y value based on a given x value. Please note that it does not work the other way around. You cannot take a given fuel consumption and work backwards to predict the rail cars. You just cannot do it. Algebraically, maybe you can, but mathematically, by the statistics of it all, does not work that way. All right, sorry, got a little bit off there on my screen. All right, so next up, you need to be able to interpret the slope. Guarantee that you're probably going to have at least a multiple choice question that covers this, or maybe even an FRQ question that covers this. Interpreting the slope. All right, you need to be able to do this in context. So this is a very generic answer, but you need to be able to do it in context. All right, as the x value increases by 1 unit, the predicted y value increases or decreases if it's negative by, well, that's your slope, right? Your slope goes right there. So for my problem, the slope was 2.1495. Now, what this tells me is that as the number of rail cars increases by 1 car, the predicted fuel consumption increases by 2.1495 units of fuel. What I tell my students to do is make the slope a fraction. When you think about slope back in middle school, the bottom is always the y, oh boy, I can't believe I said that. The bottom is always the x's, the top is always the y's. So this actually now makes sense. For every 1 x, the predicted y is the 2.1495. So, as the number of rail cars goes up by 1 rail car, the predicted fuel consumption increases by 2.1495 units of fuel. You also might be asked to interpret the y-intercept. That should be fairly easy as well. The y-intercept again is a or b sub 0. For us, that was 10.677. The y-intercept is when the x value is 0, it's the predicted y value is blank units. So that is where you actually fill in the y-intercept. So in context, that would say when a train has 0 rail cars, the predicted fuel consumption is still 10.677 units of fuel. That makes sense because even a train pulling nothing behind it, it still is a train that needs fuel to run. So make sure you can do all of that interpretation in context. Please practice that. Guarantee it comes up on at least a multiple choice question. All right, now another thing that is often covered on the AP Stats test is a linear model appropriate for your data? Meaning, if I'm going to use a line for my data, is using a line the right thing to do? Well, there's 2 really easy ways to check this. Number 1, the scatter plot should look somewhat linear. So if we go back to our scatter plot for rail cars versus fuel consumption, as long as you think that the data looks somewhat linear, that's one step closer to saying, yeah, I think using a line is appropriate. The second thing that you should always check is what's called a residual plot. Now, that's what I have right here is a residual plot, but let's talk a little bit about residuals. A residual is the distance between the actual y and the predicted y. So this red line is probably not the best line I've ever drawn, but imagine that red line was the line of best fit. A residual is the distance between the actual point and the line. So this distance right here is my residual. It's basically how far you're off, right? I mean, the line was used to make a prediction. The point is what's real. So the distance between them is how far I'm off. It's kind of like air, right? It's just like, okay, I made a prediction and I wasn't exactly perfect, but I was close. And some residuals will be very small. Like if you look at this residual right here, that's very small residual. The truth was just a little bit below my line. This residual right here almost looks to be zero. It looks to be dead perfect, right? And some residuals are a little bit bigger, like this residual. Again, those are residuals. It's the actual y value minus your predicted y value. So if you take a look at a residual plot should show nothing. That's a good thing. A residual plot that shows nothing is a good sign. Because if your line truly goes through your data, you should have positive and negative residuals. Some points will be above the line, some will be below. And if you look at this residual plot, this dotted line represents 0, showing some positive residuals above it, some negative residuals below it. And again, you should also have a mix, because early on you should have some positive and some negative residuals. In the middle, you should have some positive and negative residuals, and even at the end, you should have positive and negative residuals. So a residual plot that shows no pattern is a really good thing. If you have a residual plot that shows a very consistent pattern in your residual plot, that is a sign of a curve in your scatter plot. So that means your scatter plot probably had a giant curve to it. Maybe you just didn't see it. So to make sure a linear model is appropriate, your original scatter plot should be somewhat linear, and a residual plot should show nothing. All right, is a linear model reliable? This is another really important question that comes up a lot as well. There's two ways to make sure that your model is reliable. So remember, if I'm going to use this model to make predictions for a y, right? If I'm going to plug in how many rail cars my train has to predict the fuel consumption, I wanted it to be a good prediction, right? I mean, don't I want it to make a good prediction? Well, there's two ways that you could check how good that prediction is going to be. One is with R squared. R squared is called the coefficient of determination. This is R squared. Remember when we used our calculator here? Stat calc number 8. When we went and calculated our line, we actually got R squared right there, 0.967. R squared is a percentage, right? So it's about 97%. So R squared is the percent of variation in the y variable that is actually explained by the variation in the x variable. So this means that 90% of the variation in fuel consumption is actually due to the variation in rail cars. That's a strong connection. That shows that my two variables have a very, very strong connection, and that one definitely impacts the other, which means my equation is going to be very reliable. So 97% is a really good R squared value. You're typically never going to have to calculate R squared. Most of the time, they'll give it to you. You just have to be able to interpret it. All right. The next value that helps us understand the reliability of a line is the standard deviation of the residuals. Now, on a computer output, this is going to be just called S, the standard deviation of the residuals. You know, don't worry about calculating S. Honestly, you'll never be asked to calculate S. You just have to be able to interpret it. And I actually think it's pretty easy. So basically, when you make predictions with your least squares regression line, right? When you plug in a number of rail cars to predict the fuel consumption, you're probably not always going to be perfect, right? Your predictions are always going to be a little bit off. Well, that's what they are, predictions. Well, how far off you typically are, that's the standard deviation of residuals. So the standard deviation of residuals tells you how far your predictions are off from what's real. And obviously you want that to be very small. A small standard deviation means that typically your predictions are close to what's actual. So that's why we like small S values. But keep in mind it's all relative to the problem. If you have an S value of 4, right, and you're trying to predict somebody's height and you're only off by 4 pounds, heck, that means you're doing pretty good. If you're predicting somebody's height and you're only off by 4 pounds, that is a very small standard deviation. But if I'm trying to predict the weight of mice and I'm off by 4 pounds, that's a lot. So you do have to take context into account as well and units. So if I'm predicting the weight of mice and I'm off by 4 pounds, I'm not doing a very good job predicting the weight of those mice. But if I'm measuring elephants or humans, I'm doing a great job. So please take that number into context. All right, what I kind of wanted to end here was one final problem where we could kind of do a new problem and kind of just talk about everything real quick here. So exercise psychiatrists are investigating the relationship between lean body mass, so how much lean body mass you have in kilograms, and your resting metabolic rate in calories per day. Now, you might not understand what all this stuff is, resting metabolic weight, lean body mass, but who cares? If you're asked to create a line of best fit, all we know is this. Right here, mass is my X variable, which means I'm trying to predict your metabolic rate. I'm trying to predict your metabolic rate based on your mass, how much you weigh, your lean body mass. Right next to the word constant is always your y-intercept, 264, plus right next to the word mass, or which is your X variable, is going to be your slope, 22.563 times X, which is, again, mass. So if you give me your lean body mass, I will plug it in for the mass here, I'll multiply and I'll add, and I will predict your metabolic rate, how many calories per day you metabolize, okay? So that's how this works, right? But look at the R squared. That's a really low R squared. 55% of the variation in metabolic rate is actually due to your body size. That shows that there's not a strong connection here. And look at your S value. When I make predictions, when I try to predict your metabolic rate, I'm typically off by 144.9 calories per day. Now, for some people that might be like, oh, that's not that much, but I don't know, if I'm trying to predict how many calories per day you're going to burn off, that might be a lot to be off by. Don't ever worry about R squared adjusted, it'll never be needed. All right, now the other thing you could be asked is to interpret the slope. So remember, I'm going to take the 22.563, I'm going to put it over 1. The 1 is always the X, the actual slope value is your Y. Remember what everything is measured in here. Mass is measured in kilograms, and Y is your calories per day. So what this interpretation would be is that for every 1 kilogram of body mass that I add to your weight, that is going to increase the metabolic rate predicted by 22.563 calories per day. So it's for every 1 X, it is what we predict the Y to change by. That is how you interpret your slope. So sorry that this video is a little bit messy and very quick, but there's a lot of topics here in this unit, and I just wanted to give you a quick, roughly 20-minute video to recap it all so you could be ready for your test.